Have you ever wondered what makes a lemon so sour it makes you pucker up? Or why soap feels kind of slippery between your fingers? Well, that's not magic, it's chemistry. Today, we're diving deep into the world of acids, bases, and salts. These are the invisible forces behind stuff you see, touch, and even taste every single day. Right? That sour punch from a lemon, that slightly bitter taste if you've ever accidentally gotten baking soda in your mouth, that sharp hit of salt. These are all clues from the chemical world. Our tongues are telling us something. We know acids are sour and bases are bitter, but what's really going on at the molecular level? Well, that's exactly what we're about to find out. So, here is our game plan. We'll start with the basics. What even are acids and bases? Then we'll put on our detective hats and see how you can tell them apart. After that, we'll get into the action with chemical reactions, get a handle on the super important pH scale, and finally, we'll check out some of the most useful salts that are literally all around us. All right, first things first, what actually makes something an acid or a base? It all boils down to what they do on a chemical level. Okay, here it is, the side-by-side comparison. Acids, think lemon juice or vinegar, are sour, and they turn a special paper called blue litmus paper red. The real reason for this, when you put them in water, they release hydrogen ions, these little H+ particles. Now, bases, like soap or baking soda, are the total opposite. They're bitter, they turn red litmus paper blue, and they release hydroxide ions, that's OH-. These ions, H+ and OH- are the key players. They're responsible for everything. But wait, it gets a little more complex. Not all acids and bases are created equal. Think of it like this. Strength is all about the power of one single molecule to release its ion. Concentration is about how many of those molecules are crammed into a solution. So you could have a really strong but dilute acid, like one drop of super powerful acid in a huge bucket of water, or you could have a weak but concentrated acid, like a thick vinegar. They behave completely differently. So if we can't, and let me be clear, we definitely should not, go around tasting things to see if they're an acid or a base, how do we figure it out safely? Well, chemists have a secret weapon: indicators. An indicator is basically a chemical spy. It's a special substance that changes its color, or even its smell, to send us a clear signal when it runs into an acid or a base. It's pretty much how we make the invisible visible. And here are some of the most common ones in action. We've already talked about litmus, that classic red for acid, blue for base switch. But get this, even the turmeric in your spice cabinet is an indicator. It stays yellow in acid, but turns a deep red in a base. Pretty cool, right? In the lab, you'll see chemists using things like methyl orange and phenolphthalein for really dramatic, impossible-to-miss color changes. And it's not always about color. Olfactory indicators actually use our sense of smell. Take vanilla essence, for example. In an acid, it smells just like vanilla. But if you put it in a base, the smell completely disappears. Gone. Clove oil works in a similar way. It's a really clever trick for situations where a color change just isn't practical. Okay, so we know what they are and we know how to spot them. Now for the really exciting part. What happens when acids and bases start reacting with other stuff? A really classic reaction is what happens when you mix an acid with a metal. Picture this. You drop a small piece of zinc into some hydrochloric acid. You'll immediately see it start to bubble and fizz. So what's going on? The acid is literally dissolving the metal to create something called a salt, in this case, zinc chloride. And all those bubbles? That's pure hydrogen gas being released into the air. So how do scientists know for sure which gas is being made? Well, they have a couple of really cool simple tests. To check for hydrogen, you just bring a lit match or candle near the bubbles. If you hear a distinctive pop sound, you've got hydrogen. For carbon dioxide, which you get from other reactions, you bubble the gas through something called lime water. If the water turns cloudy and milky, that's your CO2. And now for the main event, the neutralization reaction. This is the ultimate showdown. What happens when an acid and a base finally meet? They don't just mix together, they react to completely cancel each other out. And in the process, they create two very stable neutral things: a salt and good old water. This single reaction is the key to understanding where all these useful salts come from. Okay, we've been using words like strong and weak, but how we actually put a number on that? For that, we need the universal ruler for acidity and basicity, the pH scale. The entire scale, everything about it, is built around one single number: 7. A pH of 7 is perfect neutrality. Think pure water. So the scale usually goes from about 1 to 14. Anything below 7 is an acid, and the lower the number, the stronger and more corrosive it is. Anything above 7 is a base or alkaline, and the higher you go, the stronger the base. But here's the wild part. The scale is logarithmic. That means a pH of 3 is actually 10 times more acidic than a pH of 4. And those colors you see? That's what a universal indicator would look like at each level, giving you an instant visual idea of the pH. And this isn't just some abstract lab concept. pH is absolutely critical to our daily lives. Your own body has to stay in a super tight pH range just to function. When rain becomes just a little too acidic, we get acid rain, which can devastate entire ecosystems. And your dentist is always talking about tooth decay? Yep, that's a pH problem too. It starts the second the pH in your mouth drops below 5.5. This stuff matters. So we learned that when acids and bases neutralize each other, they make salts. Now, let's look at some of the most common and important salts that we rely on in our homes and in major industries. And no, we're not just talking about table salt. First up, we have sodium hydroxide, also known as caustic soda. This stuff is an absolute workhorse in the chemical industry. It's a key ingredient for making soaps and detergents. It's used to manufacture paper, refine oil, and even to make certain pesticides. It's everywhere. Next is bleaching powder. The name gives away its biggest job, right? It's used to bleach cotton and other fabrics in textile mills, but it's also a powerful disinfecting agent, which is why it's used to purify the water that comes out of our taps and keep it safe to drink. Here's one we all know and love: baking soda. This salt is a superstar. In the kitchen, it's what makes our cakes and bread rise up and get all fluffy. Because it's a mild base, it works great as an antacid to neutralize stomach acid if you have heartburn. You'll even find it inside certain fire extinguishers. Now, similar to baking soda, but much stronger, is washing soda. This is a heavy-duty cleaning agent used in making glass and soap. But its real superpower is water softening. It's amazing at removing the minerals that cause hard water, which helps our laundry detergents work way more effectively. And finally, we have plaster of Paris. If you've ever broken a bone, you're familiar with this one. It's what doctors use to make a cast. But it's also used by artists to make sculptures and decorations, and by construction workers to create those perfectly smooth surfaces on walls before painting. Just add water, and this powder becomes a hard, durable solid. So there you have it. From the acid in your medicine cabinet and the baking soda in your fridge to the very soap you use to wash your hands, the world of acids, bases, and salts is truly all around us. So the next time you clean a stain or see something fizz, maybe you'll see the amazing hidden chemistry at play. Thanks for checking out this explainer with us.